In this video I want to talk about how to find the derivative of a quotient of two functions, and this is called the quotient rule, very similar to what we had for the product rule, which was the product of two functions. So we can define this big H of x to be the quotient of f of x over g of x. So for example, we might define h of x to be x over e to the x. Alright, so first I want to begin, like I did with the product rule, explaining how the quotient rule doesn't work. Because if we can remove that temptation, hopefully it'll help us to remember that, how it actually does work. So the temptation here is what we would the way that we would like the quotient rule to work, but it doesn't, is that I could just take the derivative with respect to x of x and take the derivative with respect to x of e to the x. So the derivative of x is 1, the derivative of e to the x is e to the x. All right. That would be nice if it worked out that way, but unfortunately it does not. So don't do that. Don't fall into that temptation. It's a little bit more complicated than that. So we're going to look at in this lecture then, well, how would we actually do it? So the first thing is I am still looking for h prime, it's just that that's not what it is. So let's go back to our definition. So h prime of x is the limit as h goes to 0 of h of x plus h minus h of x over h. All right. But this right here is how we've defined h of x. So let's just rewrite that then. The limit as h goes to 0. And so here I'm going to replace h with f over g. All right. So this is f of x plus h over g of x plus h minus f of x over g of x, replacing h, all over h. All right, so the next thing to do is let's try to get a common denominator, right? The common denominator up here would be the product of these two. So now I'm going to just drop the limit for the time being and kind of work with this expression until we have something that we can apply the limit to and get the result. So my common denominator in the numerator would just be the product. It would be g of x plus h times g of x, all right? And then in order to get that common denominator, I'd have to multiply g of x plus h by g of x, so I have to do the same thing with the numerator. So that gives me f of x plus h times g of x. And on this side, I would have to multiply by the g by g of x plus h, so I have to do the same thing over here. So I have minus f of x times g of x plus h. All right. And instead of writing this as complex fraction, I'm just going to, we can see that dividing by h is the same thing as multiplying by 1 over h, which really just kind of puts all of this stuff down in the denominator. Now comes the step that's a little bit less intuitive, but just like we did for the product rule, we'd like to be able to separate this out into things that are beginning to look like the derivative of f and the derivative of g, because it makes sense that the derivatives of these individual functions will probably be part of the derivative of this function that's the quotient of the two. So what I'm going to do now is rewrite this. So I'll rewrite the denominator just as h times g of x plus h times g of x. Let me kind of keep that separate, and here's my h. All right. Now up here what I'm going to do is I'm going to insert something in between these two, like I did with the product rule. So the first part I'm going to leave alone, that's f of x plus h times g of x. And what I'm going to insert, I'll use a different color for this so we can kind of see what I'm putting in here. I'm going to subtract f of x times g of x, and then I'm going to add f of x times g of x. All right. Then I just have, let me extend this. I just have this piece right here, so that's minus f of x times g of x plus h. Just fit it on there. Okay. So what I've essentially added here is 0, right? So I can do that without changing the original expression. And the reason I'm going to do that is I'd like to see something with an f of x plus h minus f of x and a g of x plus h minus g of x. By introducing these terms, we can begin to, so here's my f of x plus h, here's the f of x, here's a g of x and a g of x plus h. So let's rework this a little bit. So now, well, the first thing to notice is, again, I'll use a third color here. If we group these right here, notice I have this common term of g of x that I can factor out. So let's do that on the beginning of the next line. I'm going to pull out a g of x times f of x plus h minus f of x. Now, on this other side, because I would really like to have g of x plus h minus g of x, I need to change the signs here. But I can't actually change the signs without, I can't just change the signs arbitrarily. But what I could do is I could basically kind of factor out a negative here. In other words, I could write this as, minus f of x g of x plus h minus f of x g of x. And that gets in there, right? Okay, does that make sense? Because now, if I subtract this whole thing, this is negative, just like it's supposed to be right here. And then the minus and negative makes this positive, all right? So that will work. And notice again, I've got this common factor of f of x that I can factor out. Okay, so I'm going to bring down, that's going to be minus. I'm going to pull out my f of x, and I'm going to be left with g of x plus h minus g of x. All right, and you could expand this back out and see that we actually do, that the signs do agree here. It's just basically kind of factoring out a -1. All right, but we wanted it to be in this form and in this form because that's what the definition of the derivative looks like. And then the denominator is unchanged. All right, so actually just kind of continue that line here, and downstairs we've got g of x plus h times g of x times h. Now, I'd like to get rid of this h. Really, where I want the h is, I want the h underneath here and underneath here, right? Because then when I take the limit, this will become f prime, this will become g prime. So one way to take care of that is I can multiply by 1 over h over 1 over h. So that gets rid of this one because 1 over h times h is just 1. And then this will allow me to introduce this h in the denominator of this term and this term, right? It multiplies through. It distributes across, so I would get an h in the denominator here and an h in the denominator here. So let's look at that for our next step. So I would end up with g of x, and then I would have this f of x plus h minus f of x, and then this h distributes over to that denominator. So I have this minus f of x, and then I would have it here, right? So so this goes in this denominator here, g of x plus h minus g of x over h. And then downstairs, like I said, these h's multiply to 1, just leaving me with g of x plus h times g of x. All right, now things are looking up, right? Now is the point where we want to bring that limit back. Limit as h goes to 0. So without breaking this up into a bunch of individual limits, g of x is constant with respect to h, so that's just going to give me g of x. Then if I take this limit, then I know that's going to be f prime. It's important to note that f and g are differentiable functions. Those are the conditions for the quotient rule. So I know that f prime exists. In other words, I know that limit exists, so that's f prime. So let me just start writing this down now. So I'm going to get g of x times f prime of x minus, and again, limit of f of x as h goes to 0 is just f of x because there is no h in it. And this limit, when I apply the limit as h goes to 0, that's going to be g prime. And down here, if I let h go to 0, this just becomes, because this is continuous with respect to h, I can just substitute 0 for h, and I get 2g of x's, or g of x squared. I just want to write this in a way maybe that would be easier to remember. If I have f divided by g, and I'm taking the derivative, it's g f prime minus f g prime over g squared. That is the quotient rule. All right. A little mnemonic device that some people find helpful is to write it as low d high minus high d low over low squared, right? So where if you have f over g, this one's high because it's in the numerator, this one's low, so low d high, where the d represents the derivative, so low d high minus high d low over low squared. So let's go back to the original function that we looked at. So we had x over e to the x. Let's apply the quotient rule here. So h prime of x, all right, so it's going to be the denominator times the derivative of the numerator, and the derivative of x is 1, minus the numerator, which is x, times the derivative of the denominator, and derivative of e to the x is e to the x over the denominator squared. Okay, we can simplify this a little bit. This is e to the x minus x e to the x. And if you recall, when I raise a power to a power, I can just multiply, so that's e to the 2x. I could also factor out an e to the x and even cancel if I wanted to, but I'm just going to leave it like that. That's more of an algebra problem, and this is a calculus lecture, so I'll let you simplify that as far as you like. All right, so now what I would like to do is just go through a couple more examples of how to use the quotient rule. I mean, it's not, let's look at it again. It's not as simple as the product rule. And one thing I do need to point out is here order matters, right? With the quotient rule, so let's just remember what the quotient rule is. So if I had f of x times g of x, and I wanted to take the derivative of that, I could do f prime g plus f times g prime. I could switch these back and forth because order doesn't matter for addition. I could also switch these back and forth, right? I could have g times f prime and g prime times f. So order didn't really matter here. But if I'm doing the quotient rule, it certainly does matter, because now I have g. Well, here the order doesn't matter, right? I could do f prime first and then g because this is multiplication. But here, this subtraction, if I get these backwards, and I'm basically finding the negative of the derivative, right? So then this is f of x g prime. So I just wanted to point that out, that order does matter for the quotient rule. It doesn't matter for the product rule. Okay, so let's see another example. Let's say we have y equals x squared plus x minus 2 over x cubed plus 6. So dy dx, just straightforward application of the quotient rule. We have the denominator function times the derivative of the numerator. So the derivative of this is going to be, that is 2x, that's 1, and that's 0. So I'm just left with 2x plus 1 minus the numerator function plus x minus 2 times the derivative of the denominator. Well, the derivative of this is 3x squared, and the derivative of 6 is 0. So that just gives me 3x squared all over x cubed plus 6 squared. So that is that's certainly ugly, and it's messy looking. I guess technically I should have a parentheses on there to indicate that all of this multiplies all of this and not just the 6. All right, so you have to be careful with your notation there, but ultimately that's it. You don't have to simplify this. In fact, for the purposes of grading, it's easier just to leave it this way, because then I can see that you know how to apply the quotient rule. If you needed to do more with this, for example, if we're going to take the derivative of this, which we'll talk about in the next lecture, and taking the second derivative, then it might be useful to clean this up a little bit before we take the derivative again. But in general, no need to simplify here. All right, that is not the point. Like I said, that's an algebra problem, not a calculus problem. All right, let's do another example in, I don't know, let's say blue. Okay, so let's say we have this function, we'll call it g of x. Not to be confused with the g of x in the denominator. That was just some general function. Now I have this specific function, which is 3x squared minus 2 over 4x cubed plus 1. And what I would like to do is find the equation of the tangent line at x equals 1. So first I need the slope of the tangent line, right? And the slope of the tangent line at x equals 1 is g prime of 1. So what we'd like to do is find g prime of x and then just substitute 1. All right? So let's look at how we would do that. G prime of x, again, this is a fairly straightforward application of the quotient rule. So I'm going to take the denominator times the derivative of the numerator. So this is going to be 6x, and then the derivative of negative 2 is 0, so that's just going to be 6x minus the numerator, 3x squared minus 2 times the derivative of the denominator, which is going to be 12x squared, and the derivative of that is 0, so that just leaves me with 12x squared over the denominator squared. Now I could simplify, but again, I'm not sure how helpful that would be to simplify this algebraically, because ultimately I'm going to substitute 1 for x, and that will, I think it'll be easier to simplify this after we substitute 1. So g prime of 1 is going to be 4 times 1 cubed plus 1 times 6 times 1 minus 3 times 1 squared minus 2 times 12 times 1 squared, all over 4 times 1 cubed plus 1 squared. So now we just have a little bit of arithmetic to do. Given that we're using the value 1, it's not so bad. So this is 4 times 1 cubed, that's just going to be 4 plus 1 is 5 times 6 minus, and so here I have 1 squared is 1 times 3 is 3 minus 2 is 1, and then that of course is just going to be 12. And then down here, well, this is the same expression as this, which we found to be 5, so that's 5 squared. So one more step here, we have 30 minus 12 over 25, which is 18 over 25. So that is the slope of the tangent line. To find the equation, we also need a point on the tangent line, so we can go with the point of tangency. In other words, what is g of 1? When x is 1, what's the y value? Well, that's going to be 3 times 1 squared minus 2 over 4 times 1 cubed plus 1. Well, that's 1 over 5. So this is my x value. There's my y value, so the point is 1/5. Here's my slope, so I have y minus 1/5 equals 18 over 25 times x minus 1. There's the equation of my tangent line. Okay, so that was one more example. And then I'm going to finally do one last example using the quotient rule. Give that color a breather. Let's try something like h of x equals 3x squared plus 2 times the square root of x over x. All right, so h prime, again, is the denominator times the derivative of the numerator. So this first piece is just going to be 6x. And then here we need to remember what the derivative of the square root of x is. So if you recall, the derivative of the square root of x is 1 over 2 square root of x. All right, we've done that in previous lectures, so I'm not going to repeat that here. But then I have 2 times right? The derivative of a constant times a function is the constant times the derivative of the function. So I take 2 times this, and notice that the 2 here will cancel with this 2, and I'll be left with 1 over the square root of x. All right? So that's for the first half, the bottom times the derivative of the top, and then I have the top, 3x squared plus 2 square root of x times the derivative of the denominator, which is just going to be 1, over the denominator squared. So there you have it. Again, I'm not interested in simplifying this. That is the derivative. What I want to point out here, though, with this example is that the quotient rule isn't always the simplest way or the easiest way to find the derivative. It'll certainly always work, but sometimes we can simplify what we started with in order to make our lives a little bit easier. So if I take h of x, and I'm just going to rewrite this as 3x squared over x plus 2 square root of x over x. Does it make sense? Hopefully that this is equivalent to this, right? I have a common denominator here, so I could combine them into one term. Well, I can go the other direction as well and separate this into 2, right? Now, this first piece simplifies just to 3x, and if we think of x as square root of x times the square root of x, then I can divide out one of them, and I'm left with 2 over the square root of x. All right, so this is algebraically equivalent to what I started with. So this looks like it's much simpler to take the derivative of, especially if I rewrite this. So let's rewrite this one more time. Remember that square root of x is x to the 1/2, and then I can take, if it's in the denominator, I can rewrite it as 2 times x to the negative 1/2. Now I've basically rewritten everything as basically x to some power, and I can just use the power rule. So now h prime, if I'm using this as h, well, the derivative of 3x is 3. The derivative here, using the power rule, I take the 2 and I multiply by negative 1/2. I get negative 1, so that's negative, I'm not going to write 1, we don't usually do that, negative 1 times x, and then I have to subtract 1 from that, so that would give me negative 3/2. So what I want to, again, the point of this example was to show you that first, if you can simplify this, sometimes you can avoid the quotient rule, which is a lot more complicated. So not only was taking the derivative much simpler, but I ended up with something that's much nicer in terms of it's much simplified. We certainly could work with this algebraically and get it down to here, but that's a lot more work than I want to do. If you like to do that sort of thing, then knock yourself out. But again, it kind of depends on what we're going to do with it, right? If I had to take the derivative of this, then this is a whole lot easier to take the derivative of, right? If I want to define the second derivative, so here's a sneak preview of the next lecture. If I want to find the second derivative, this is going to be very simple to take the second derivative of. This, not so much. So, just take a look at what you're doing. Think about what you're doing before you just apply these rules mindlessly.